Hello students, I wanted to talk to you in the context of AC electronics. We're going to spend just a few minutes talking about AC in a nutshell. And we're going to talk about what you already know. If you've studied DC electronics, you know these four concepts here. You know that voltage is a force, and that we can consider voltage a pressure, a force. Also, we know that current is the flow of electrons. So the current, we think about the idea of something flowing, which is electrons. Resistance is the opposition to that flow. It opposes the flow of electrons. And then power is the idea that there is something being done with work. Work is being done. Energy is being converted. So that's the idea of power. So these are the four things we understand about DC electronics. And we're going to take those four ideas and talk to you about the context of AC circuits. So when I talk about a particular DC idea when I talk about DC voltage is that's going to be discrete voltage. It's either on or off. So if I have a battery and that battery is a car battery, it's going to be 12 volts. If it's a AA battery, it's going to be 1.5 volts. And we're going to continue to look at that. And then we also have AC current. So AC current is always changing. It is going positive and it's going negative. And that change is going to be contingent on at least two things, and those two things are going to be the time and the frequency. And we'll talk more about that when we actually deal with that into the class. There are at least 5 ways I can measure an AC voltage. And in this class, we're going to primarily focus on 2 of the ways that we measure AC voltage. That's going to be what we see on the O-scope at the end of the course, and of course what we see on the digital multimeter. So if I look at a sinusoidal wave, if I have drawn a sinusoidal wave and I'm looking at it here, these are sort of what we're looking at here. This is just a simple diagram of a sinusoidal wave. If you look up here where it says T, that's a time base that looks at the sine wave from the beginning to the end. And then we have VPP, stands for voltage peak to peak. And then we have voltage peak over here, which is just a positive going thing, just half of the voltage peak to peak. And then we have voltage RMS, which is a certain percentage of that, and voltage average, which is a certain percent of that, and then voltage instantaneous. So if I'm designing these particular ideas, if I'm defining these ideas, is that my voltage peak to peak is a voltage that is measured from the highest positive peak to the lowest negative peak. That's my voltage peak to peak. So the very top of that sine wave to the very bottom. And then if I want to talk about voltage peak, I'm just talking about half of the voltage peak to peak. So that's going to be 1/2 of voltage peak to peak. Voltage RMS is what my digital meter reads. The voltage RMS right here, that's going to be about 70%. We take the voltage peak and multiply it by 0.707 to get that particular answer for voltage RMS. That is what your voltage, your digital multimeter will read. The voltage average is a lot of times used with the power industry, and that's going to be sometimes we call it voltage average. The voltage is 0.637% of the voltage peak. And then the instantaneous voltage can be a point anywhere on that sinusoidal or the sine wave. We can pick any single point. I can take the sine wave. I can say, okay, what is the voltage at this point here? And you can tell me what the voltage is at that particular single point and give me a phase angle of what that means, okay? Now we get back to these 4 ideas again that we talked about at the original part of this talk here, is that there's 4 things. There are at least 4 things we can talk about. Voltage is still a force or a pressure when I talk about AC electronics. Even though that sine wave is moving up and down, there is a force in consideration for that. And any flow of electrons would be considered current. So current flow, it flows in both directions in AC. It goes to the left, goes to the right, it goes up, it goes down. It goes positive, it goes negative. So the flow of electrons go in both directions. And again, when we talk about this idea, the opposition of current in DC, we talk about resistance. When we're dealing with that in an AC circuit, we deal with impedance. We'll get more to that in just a second. But the impedance is the opposition to the flow of current. And then power is some type of work. We're converting energy from one particular thing to the other. Again, if we look at the bottom part of this where it shows what these things are, there's voltage, current, impedance, and power. The symbols for those are going to be V, I, Z for impedance, and P for power, VIZP. The unit of measure for those are volts, amps, ohms, and watts. And then the unit of measure in symbols is going to be VA, the omega sign for ohms or impedance, and then watts. So those are the four things that we will study in AC electronics. Now, we're going to change the circuit configurations. We're going to introduce a couple of different components, and we're going to calculate the impedance of those components and see how they affect our circuit. So let's go to the other end of the room. Let me walk you down there. And as we go to the other end of the room, we're going to talk pretty much exclusively about impedance. Now, impedance is going to be the symbol Z again for impedance. And impedance is measured in ohms. And that's this Z symbol I have right here. So this Z symbol. So there are at least three things we can put under that Z. Resistance, and resistance is a linear function. So resistance, we would consider resistor or anything that introduces resistance to the circuitry in that particular device. Then we have this term called X of L. That stands for inductive reactance. The letter L stands for inductance. The X stands for reactance. So reactance, whether it's inductive or capacitive, is measured in ohms. So we have X of L for inductive capacitance, or reactance, sorry, and X of C for capacitive reactance. And those things are contingent on what's going on with the frequency and the unit of measure for that particular device being used. Resistance, again, is a linear function. Now, there's a couple of equations we're going to introduce into this class, and that's going to be later on. But I just want to introduce to you, when I talk about this, just to introduce a couple of ideas. So we have this equation up here, which stands for the inductive reactance is going to be equal to 2 pi times frequency, and then times the inductance. So the 2 pi, those are just mathematical constructs. Those are actually constants. So 2 is just the number 2 times pi, which is 3.1415926. I can simply just say that the constant of those two things multiplied together is close or approximately 2.68. The frequency will be given contingent on what the power supply is set up, as well as the value of the inductors. Now, inductors are measured in henries, and the unit of measure for henry would be an H, and then frequency is going to be measured in hertz, and that's a capital HZ. So we know what hertz is. And then let's just do a problem. Let's say that the inductor is 100 millihenries, or 0.1 Henry. So 100 millihenries. Okay, I just mathematically reduced it down to 0.1 Henry in the equation, multiplied by 60 hertz. Then the ohmic value for my X of L in this case is going to be 37.7 ohms. So that's how you would do the math on that. So if you have a small inductor, you have a small and a low setting for frequency like 60 hertz, that's your household frequency. And then your ohmic value is going to be small. There's not a lot of impedance or a lot of reactance there. Now, what happens if I change my frequency from 60 hertz to 60,000 or 60,000 hertz or 60 kHz? So I'm going to increase my frequency by 1,000 times, and then I redo the problem. So X of L would indicate that as when I do my problem again, is my frequency increases 10 times, so does, in this case, the inductive reactance or the impedance for the overall circuitry. Okay, so it goes up 1,000 times. So in the green down here at the bottom, it says when frequency increases, the ohmic value goes up. And then finally, if we look over here at the capacitive reactance, that's 1 over 2 pi times, so 2 times pi times the frequency times the capacitance. And that's going to be an inverse. That's going to be over 1, or going to be under 1, okay? So again, my 2 pi is just a mathematical constant, which is 6.28 in this case. Frequency is whatever value have the power supply or the trainer set to. And the capacitance is going to be a given value. That capacitance is measured in a farad. A 1 farad capacitor is about the size of a Monster drink. So we are usually measuring farads in either microfarads or more commonly in picofarads. Okay, so in this case, we're doing a problem, and our capacitor is measured in farads. And if I give you a circuitry to where the capacitor is equal to, I want to change this to picofarads. So remember, pico is 10 to the minus 12. So I'm changing that to picofarads. So if you have a capacitor that's set at 1 picofarad, and my frequency starts out at 60 hertz, then when I do the math on that, is that I get a high reactance of 26 or 26.5 megahertz. Now what happens when I change my frequency to 60 hertz is that I get a value that is 1,000 times smaller. It's 26.5 kilohertz. Okay, so in this case, when I increase the frequency, is that my reactance goes down. So that's the inductors and capacitors oppose each other when you're changing the frequency. Now we're going to spend some time when we look at the trigonomic functions that happen with inductors and capacitors when we put them in circuits together. We're going to do the we're going to look at some of the trig that's involved. We're going to look at some of the reactances. We're going to look at the relationship of the reactance to the resistance to whether it's the power, voltage, or current, depending on the configuration of the circuit. So this basically is AC in a nutshell. This is not comprehensive. There's some other things that we'll go into as we get further into the class. But I want to introduce you to some of these concepts and give you some confidence that since you do know some DC electronics, we can apply some of those principles to AC electronics. And I look forward to seeing you in the laboratory.